Hi, this is Rohan from educator.ai. Let's dive in. Every time a language model writes a word, it is really rolling a very special pair of dice. Temperature is the single knob that decides how loaded those dice are. In this video, we will build a precise mental model of exactly what that knob does to the numbers. If you have called a model twice with the same prompt, you have seen it. One run is safe and repetitive, another is wild and surprising. Turn temperature down and it becomes almost deterministic. Turn it up and it starts to ramble creatively. As a developer, you will set this value constantly, so it pays to know exactly what is happening underneath. Before any word is chosen, the model produces one raw score for every token in its vocabulary. These scores are called logits. A logit is just a number. The bigger it is, the more the model favors that token. But logits are not probabilities yet. A function called softmax turns that list of scores into a proper probability distribution that sums to 1. Here is the mental model to hold on to. Think of temperature as a dimmer switch on the model's dice. Turn it low, and the favorite token shines so brightly, it almost always wins. Turn it high, and every option lights up together, so even unlikely tokens get a real chance. Now let's see that happen to the actual numbers. Let's take a tiny example. After the prompt, the model prefers cat, then dog, then a few others. At temperature 1, we apply softmax directly to the logits and get this distribution. Cat has about a 50% chance, but nothing is guaranteed. This is our baseline shape, the picture we will now stretch and squash. The mechanism is beautifully simple. Before softmax runs, we divide every logit by the temperature, T. That is the whole trick. Dividing by a small number makes the scores spread apart. Dividing by a large number pulls them together. Then softmax converts the rescaled scores into probabilities as usual. Set temperature to 0.5. Dividing by a half doubles every logit, so the gaps between scores grow. After softmax, cats laid balloons from 50% to nearly 80%. The distribution is now sharp and focused. The model becomes confident, consistent, and boring in the best possible way. This is what you want for facts and code. Now push temperature up to 1.5. Dividing by a bigger number shrinks the gaps, so the scores crowd together. After softmax, the distribution flattens. Cat's lead melts to under 40%, and rock, once almost nothing, now has a real shot. This is creativity, and also the door to nonsense if you go too far. Keep turning the dimmer down toward 0. The gaps stretch toward infinity, so softmax collapses onto a single spike. The top token gets all the probability, everything else gets none. That's just picking the argmax every step, which we call greedy decoding. Temperature 0 is not a special case, it is the natural limit of this same division. Let's prove it with numbers. We take the logits 2, 1, and 1/2, divide by t, and run softmax. Subtracting the max first is just a numerical stability trick that changes nothing. Watch the output. At temperature, a half the top probability climbs. At 1.5, it falls and the tail rises, exactly the sharpening and flattening we drew. There is a catch. Flattening the distribution gives creativity, but it also hands probability to genuinely bad tokens. We want variety among sensible words, not random garbage. The fix is to cut off the long tail before we sample. Two popular ways to do that pair naturally with temperature: top K and top P. Top K is the blunt version. Rank the tokens, keep only the K highest, and throw the rest away. Here, with K equal to 3, we keep cat, dog and fish, and dim bird and rock to 0. We then renormalize the survivors, so they sum to 1 again, and sample from just those. Simple, but K is a fixed count that ignores how confident the model actually is. Top P, also called nucleus sampling, is smarter. Instead of a fixed count, you add tokens from the top, until their combined probability crosses a threshold, say 0.8. Here cat plus dog plus fish already reached that mass, so the set stops there. When the model is confident, the set shrinks. When it's unsure, the set grows. The cutoff adapts to the shape. In practice, you rarely code softmax yourself. You pass these knobs to the API. Temperature 0.7 gives balanced variety. Top P 0.9 trims the worst tail. A common convention. Set one and leave the other at its default rather than fighting both at once. Same mechanism we drew, just exposed as parameters. 2 myths to bust. First, temperature never invents new information. It only reshapes probabilities the model already computed. Second, high temperature is not more intelligent, it is just more random. And a subtle one, even at temperature 0, output can drift across runs because of hardware and batching non-determinism. Low temperature reduces variance, it does not guarantee identical bytes. Here's your review lens. For structured or factual work, keep temperature low so the top token dominates. For creative work, raise it, but clip the tail with top P. Adjust one knob at a time. And remember what temperature actually is. A divisor on the logits before softmax, nothing more, nothing less. So the whole idea in 4 lines. Temperature divides the logits before softmax. Low temperature sharpens the distribution toward the favorite. High temperature flattens it toward variety. Temperature 0 is greedy decoding. And when you crank it up, pair it with top K or top P to keep the creativity from turning into noise. That is the dimmer switch, fully understood.